Assalamu alaikum everyone. In this video we are going to see the relationship between shear matrices and eigenvectors. Eigenvectors and eigenvalues are a pretty straightforward topic in class from a computational point of view, but few do a fine job explaining its geometrical interpretation. And to see the relationship between shear matrices and eigenvectors, we need to understand what eigenvectors and eigenvalue represent geometrically.
To start, consider some linear transformation in two dimensions, like the one shown here. It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2. Focus in on what it does to one particular vector, and think about the span of that vector, the line passing through its origin and its tip. Most vectors are going to get knocked off their span during the transformation. I mean, it would seem pretty coincidental if the place where the vector landed also happened to be somewhere on that line. But some special vectors do remain on their own span, meaning the effect that the matrix has on such a vector is just to stretch it or squish it, like a scalar. For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis, and from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis. What's more, because of the way linear transformations work, any other vector on the x-axis is also just stretched by a factor of 3, and hence remains on its own span. A slightly sneakier vector that remains on its own span during this transformation is -1, 1. It ends up getting stretched by a factor of 2. And again, linearity is going to imply that any other vector on the diagonal line spanned by this guy is just going to get stretched out by a factor of 2. And for this transformation, those are all the vectors with this special property of staying on their span. Those on the x-axis getting stretched out by a factor of 3, and those on this diagonal line getting stretched by a factor of 2. Any other vector is going to get rotated somewhat during the transformation, knocked off the line that it spans. As you might have guessed by now, these special vectors are called the eigenvectors of the transformation, and each eigenvector has associated with it what's called an eigenvalue, which is just the factor by which it's stretched or squished during the transformation.
Now that we understand what an eigenvector is, let's take a closer look at how a shear transformation works and how it is related to eigenvectors. But first, we need to draw our grid. A shear transformation fixes the vectors that are located on one of the axes, either the x-axis or the y-axis, then moves the rest of the vectors to a specific location dictated by the transformation. In this example, we will do a shear transformation on the x-axis. The transformation will fix I hat on 0, 1 and moves j hat to 1, 1. Here we can clearly see the relationship between a shear transformation and eigenvectors, where a shear transformation happens only if the transformation has only one eigenvector, and that vector happens to be either the x-axis or the y-axis. In our example, only the vectors on the x-axis stayed on their span, whereas all the other vectors got knocked off their span. And with this, I hope that we can see the relationship between shear matrices and eigenvectors and their geometrical representation. Thank you very much for watching. See you next time.